Okay, two more videos for this week. This second to last video, well, two more videos for lecture material, and then I'm going to give you the assignment in the last video. But this one, video 6, is about stepwise versus hierarchical partitioning and variance. Now, many of you who have taken my previous classes, I have all these Venn diagrams that I show you what the different sums of squares are and how they're computed. I will post those slides onto the course website, but for now I want to focus primarily on what they mean and not go through a lot of R code. I've just posted R code here, and primarily not to give the R folks a step up over the SPSS folks, but that R is very, very difficult to differentiate these. So I wanted to give the R folks a little bit of a head start. In SPSS, the differentiation between type 1, type 2, and type 3 are all just a mouse click away, and it's very easy to see the difference. So ignore this code unless you're an R user. If you're an R user, you'll have this available for download. Instead, this video is mostly an explanation of the difference between stepwise and hierarchical partitioning. Stepwise partitioning is really is an empirical method that has fallen largely out of favor in most of social and behavioral sciences. Very few statistical packages will even, well, they have it by default, but most people unfortunately unknowingly select it and they get into problems. So what is stepwise? Stepwise is an empirical selection procedure that selects predictors based upon the relative contribution in the prediction model. So there's very little control over what happens in stepwise regression, and stepwise eventually leads to, one, a selection of variables that were not a priori, nor were they theoretically justifiable necessarily. I assume that all variables are theoretically justifiable, but in this case, because the algorithm selects the variables that end up staying in the model, that is not really theory testing. And so hierarchical partitioning of variance, or at least a hierarchy of variables, has now taken priority in data analysis in social and behavioral sciences, and there's some debate as to what really happens. Now, in SPSS, there is a procedure that is called a method of enter, and what it allows you to do is select variables, and what it will do is it will incrementally add variables into your model. And that's different than stepwise regression, in that you get to specify every single variable that goes into your regression model, and then the variables are not selected empirically. Instead, they are inserted in there because you deliberately told SPSS to put those in. In R, any variable that you specify in your model formula will be included in your model. So it doesn't really matter. And that method of enter is not really technically hierarchical partitioning of variance. It is a selection procedure, however, and it's a selection procedure that enables the data analyst to select all variables that are relevant to the model. But it is not hierarchical partitioning of variance, because in that procedure, all of the parameters are estimated using type 3 sums of squares. Now, what does that mean? That means that all of the effects are estimated simultaneously. Not all of them, but all effects that are of the same level. So all main effects are estimated simultaneously, all interactions, so on and so forth. Well, in regression, we don't have effects that are of different standing, because everything is a variable. Everything is viewed as a covariate of some level, whether it's a dummy code that we're going to talk about later, or which would be like a binary variable, or whether it's a continuous variable. They're all covariates. And so in regression, there isn't the same distinction between main effects and interactions and so on and so forth. So you really have to go to ANOVA in order to get that distinction. And here's where hierarchical partitioning of the variance gets a little dicey. In regression, hierarchical partitioning of the variance needs to be done explicitly. So you need to be able to say that all of these effects need to go in this order, and that is the order in which they will be tested. So what does that mean? Well, it means that if it's hierarchically partitioned, if we think back on the Venn diagram that I had before, what it would mean is the first variable that gets entered in would get instead of getting a portion of the variance, the first variable that goes in gets its full allotment of the variance. So in other words, the first variable that gets its crack at the dependent variable, or the criterion, gets its coefficient of determination. So it gets all the variance in y available. And then what's left over is merely a partial correlation coefficient, or a squared partial correlation coefficient for each subsequent variable. So what that means is that in a hierarchical partitioning of variance, that the variance of y gets partitioned according to the entry of the variables into the model. Simultaneous, on the other hand, leaves every single variable with only a squared partial correlation coefficient. And that's bad in some respects, because what we're getting is a restriction of the amount of variance in y that we can account for when we have a lot of multicollinearity. That we're going to omit sources of variability where there's high collinearity between predictors that also overlaps with our criterion. And remember that as we were looking, if you notice here, that there's a portion of, in this case, back to the figure that you'll be able to pull up from the website, that what you'll get is a portion of common variance between x1 and x2 that's labeled as C. And that variance gets thrown away when we're trying to account for the variability in y. So what does that mean? That when it gets thrown away, it gets pooled into that same pot of variability that is unique, or residual variance, and that is the A portion. So A and C get pooled together as if they are residual variance that is never accounted for by by the regression. And that means that it limits our inquiry into y, and it underestimates or attenuates the amount of variance in y that we can explain. And that's the reason why hierarchical partitioning of variance enables us to recapture that portion of y and assign it causal priority to whichever variable we deem most appropriate, or most theoretically appropriate, or what have you. And so at this point, I'm going to stop with the distinction between stepwise and hierarchical partitioning, because what I want to do is, first I want to dispel any notion that stepwise is even a suitable procedure, and it is not. But second, dispel the notion that hierarchical partitioning of the variance is readily available in SPSS in the regression model. You need to run the GLM function and specify the types of sums of squares in order to get the different, either simultaneous, which is type 3, or hierarchical or sequential, which is type 1. In R, it's a little bit more difficult. In R, the developers claim that it defaults to type 2 sums of squares, but I've laid out all this R code to enable R users to determine for themselves what sums of squares is by default available in R. I'm going to stop here because that's going to be part of our assignment, our in-class assignment. We have one more video for this week, and that is alternative methods for dealing with multicollinearity, so stay tuned.